Project 13. Develop a practice problem worksheet and answer key video. Chapter 9. In this video, I will show you how to determine the electron domain geometry, molecular geometry, and polarity of a molecule. For this video, I decided to use SF6 as my example. It doesn't really matter which order you go into determine electron domain geometry, molecular geometry, or polarity. I just decided to start with electron domain geometry first. So to begin, first step, you would need to count all electron domains. And this electron domain is defined as any bonding or non-bonding pair of electrons. In this case, in SF6, we have 6 bonding pairs. As you can see, they are all labeled 1 through 6, and we don't have any non-bonding pairs, so I don't have any of those labeled, but each bond is counted as 1 electron domain, so we have a total of 6. So, as stated before, SF6 has 6 bonding pairs of electrons and 0 non-bonding pairs of electrons, which gives it a total of 6 electron domains. With this information that we have gathered, we can now use the Vesper model to predict the shape that the molecules will form based on each bonded pair and non-bonded pair that is extended off the central atom. So in this case, SF6 having 6 electron domains retains the electron domain geometry of an octahedral. So for my next step, I decided to go with determining the molecular geometry of SF6. Basically, you would do the same thing that you were doing as if you were determining the electron domain geometry, except you will only count the bonded electron domains. So as you see, I have the same 6 bonded pairs label, which count as the 6 electron domains, and this is what we will use to determine the molecular geometry of SF6. So as you saw on the previous screen, SF6 has 6 bonding electron domains, and with this information we use the Vesper model to predict the shape that SF6 will form just based off of the bonding electron domains alone. And as you can see, it also forms an octahedral. So in this case, because of the lack of non-bonding electron domains, the shape of the electron domain geometry and molecular geometry are the same. So the last and final step to this problem is to determine whether or not SF6 is polar or nonpolar. And to do that, we have to look at a couple different things. So when a molecule contains more than 2 atoms, in this case, SF6 contains 7, the dipole moment depends on 2 factors: polarity of each individual atom and the shape of the overall molecule. And we already determined the shape of the overall molecule in the last couple of screens back. So the first step of the polarity problem is to determine the shape of the molecule, which you've done in the last couple of screens back. So we saw that just based off of the bonding electron domains, that the shape of the molecule for both the electron domain and molecular geometry is an octahedral. And just want to keep in mind that you do want to look at both electron domain geometry and the molecular geometry when determining the shape of the molecule, and for the purpose of determining whether the molecule is polar or nonpolar. So the last and final step in determining whether or not SF6 is a polar or nonpolar molecule, we need to look at the polarity of each individual atom in the molecule. And to do this, we have to remember the electronegativity trends of the periodic table, which are as follows. Electronegativity increases as we move across the periodic table and decreases as we move down a group. So in this case, if we look at the periodic table and we look at fluorine and we look at sulfur, we can determine that fluorine is more electronegative than sulfur because it is further to the right and closer to the top of the periodic table. So in combination with the symmetry of the octahedral shape and the greater electronegativity of fluorine in SF6, we determine that SF6 is a nonpolar molecule.